So it's important for every question that you do, you start first with your free body diagram, and you start with your net force equation. Okay? Have we talked thus far about having your net force equation be up forces minus down forces? Yeah. Yes, and right forces minus left. Okay, so we know the net force can only work horizontal or vertical. All right, that's important to know. Are we on the same page with that? Okay, the net force is always going to be up forces minus down forces, or right minus left. Okay, when you're working with net force, it has to be either horizontal or vertical. All right, so let's draw our free body diagram here. Okay, it says an airboat glides across the surface on a cushion of air. Perform the following calculations for a boat on which the mass and passengers is 450. There's no friction. How much force must the propeller fan exert on the boat? Okay, so let's see here. What forces can you imagine are acting on this boat? Yeah, it floats on a cushion of air. So let's say our upward force here would be like air resistance or something pushing up on that. Okay, so we'll say F air. That's pretty ugly. Good. What direction is gravity pulling on it? Down. Is the boat moving up and down at all? No. It's gliding across the surface. It's only moving horizontal. So that cushion of air is just kind of like the normal force that's pushing it up. Okay, so it's not really bouncing up and down. It's steady vertically. Okay, so that means the force of gravity and force of air need to be equal to each other. Does that part make sense? It's not moving up and down at all, so those two have to be equal. What about horizontal forces? Are there any horizontal forces acting here?
The propeller fan.
Exactly, the fan. So we'll say force of fan. And you can label those forces however you'd like. I would choose to say force of fan. Okay? So we want to look at acceleration of the boat. Do you think this acceleration will be taking place horizontally or vertically? Horizontal. We know what the boat looks like, right? Can you imagine one of those boats that has the big fan on the back and it pushes like in the swamps? You know, that's what we're talking about here. Okay? So we're looking at horizontal here. What forces do we have in the horizontal direction? The fan. That's it. Okay, so our net force equation here, if we take right minus left, is going to equal force of fan minus what?
Nothing.
Minus nothing. Right? There's no forces to the left. So that's our only force right there. That's our net force. That's it. Are we there? We feel good about that part so far? Okay. You could put a minus 0 here if you'd like. I choose to leave it out. All right? So then we can start doing our substitutions. We can start substituting. So we know F net is also equal to what? Mass times acceleration. We want to find the force of the fan here. So we don't substitute anything for that because that's what we want to find. Force of fan. So we go back to our problem and we know we're given the mass and we're given the acceleration. So I'm going to move my equation up here. Our mass is 450. Our acceleration is 5. And that's going to be equal to force of the fan. That's how much force the fan will need to exert to get that object to move at that acceleration. And what do we get? Exactly. What are my units then if I'm solving for a force? Newtons. Exactly right. The second part says, if the actual acceleration of the fan generating the force calculated in part A is only 4.95 meters per second squared, how much friction does the air cushion exert on the boat? Okay, so now we take into account a frictional force. Okay, we're saying that we're going to keep that same net force. So our net force would then be 2250 and we want to find out how much friction does it cause. So we're going to say F net is going to equal the force of our fan, and now we need to subtract out that frictional force because that will be going in the opposite direction. Okay, so we found our new fan force, which is right here. So we're going to take then our net force. I'm going to move my equation over here. We're going to take our net force, which is 2250, equals our fan force minus, friction. Okay, so we're going to subtract this over. Subtract it over, and what do we get our frictional force to equal? 22.5. And what units does that come in? Newtons. Okay, so part C of this question is asking what upward force exerted by the air cushion on the boat. So we go back to our free body diagram, which shows us that gravity is pulling down, this air cushion is pushing up, and we know there's no vertical acceleration. So what does that mean with these two forces? They have to be equal. Okay, so we can write out our whole net equation here. F net equals up minus down, so force of air minus force of gravity. But since we know there's no acceleration, we know this is 0. So F air minus Fg equals 0. So if we move this over, we know Fg equals F air. Okay, and you guys just told me that since we know those two are equal. I just showed you the math to prove it. Does that part make sense? You guys told me that F net has to equal, that Fg has to equal F air just by your free body diagram. You knew that. But this net equation will prove it. Okay. So let me get rid of this. How do we find F sub g? There we go. Mass times gravity equals F of the air cushion. And we know our mass is what? 450. And we know gravity is 9.8. That's all you do? $4,410 newtons. Okay?
So we know that 9.8 is the acceleration.
Yeah, that's gravity. When it's vertical, that gravity's got to be 9.8. Okay? All right. Okay, so we need to read this problem carefully here, but there's a typo here where it says the period of acceleration. It should be 0.5 seconds, not 0.5 meters per second. So we'll cross that part out.
It's supposed to be time.
Yeah, it's supposed to be time. Yeah. So it's just 50 seconds. So let's think about what we need to adjust in our problem first. What does our mass need to be in? It needs to be in kilograms. So then our mass becomes 0.045 kilograms. All right, and what about our velocity here? How do we go from kilometers per hour to meters per second? Multiply by 0.2778. So to go from kilometers per hour to meters per second, we multiply this number by 0.2778. That's our shortcut that we solved for to go from kilometers per hour to meters per second. We did that a couple chapters ago. So what'd you get your velocity? 50 point, what? Okay, so we'll just call it 50. So 50 meters per second. What's the average acceleration that the ball was struck in meters per second squared. So we're solving for acceleration here. We have initial velocity, which was 0. We have final velocity, which was 50. And we have time, which is 0.50. Exactly. You could do VF equals VI plus AT. Or you could do delta V over delta T. Either way, it works out the same. What'd you get?
100.
And if we're solving for acceleration, what does that mean our units should be? Meters per second squared. Okay. What is the force exerted on the club? Okay, we're looking to find net force here. F net equals mass times acceleration. That's it. If we wanted to draw the free body diagram, all we do is we have the ball here. If it's at rest on the ground, it's going to have a normal force and a gravitational force, and then it'll have some sort of applied force that's hitting the ball. Okay, so this would be our net. Okay, so we're still doing the same thing. Okay, force equals mass times acceleration. So we have force, we have our mass, which is 0.045, and we have our acceleration, which is 100. So we get what? 4.5 newtons. Very good. And then for part C of this question, I want you to think about what Newton's third law tells us. What does Newton's third law say? Yeah, the direction. All right, moving on with number 3. A box with a mass of 9.7 kilograms experiences a net force of 41 newtons while being lifted. What's the acceleration of this box? Okay, so this problem tells us the net force. That's it. Okay, it tells us that. We don't need to worry about doing our net force equation because we know the net force, we know the mass. All it's asking for is acceleration. So what equation do we use here? Force net equals mass times acceleration. Will the acceleration be in the positive or in the negative? Which direction? Positive, right? Because it's going up. So we know it's in the positive direction. What'd you get for acceleration? And what's our units for acceleration? Very good. Okay, so for this problem, since it's hanging on that spring scale, what are the forces acting on it? Yeah, that's it. That's it. That's all there is. Okay? So, find the reading on the scale for each of the following situations. When the scale is not moving, what's that tell us that our net force will be?
0.
F net is 0. Okay? So, we want to see that our F net is only going to be our F sub g. That's what it's going to equal. Okay, if it's not moving, that's going to be our only force. So all we're solving for here is F sub g. So F sub g is mass times gravity. Our mass is 0.1. Gravity is 9.8. What units do you think for a force? Newtons. So So 0.98 newtons. What would the scale read now when it's accelerating 2.4 meters per second squared in the horizontal direction?
All the springs don't even
What if I go like this? Yeah.
How come on the last one there's not like tension?
Number 6 says the sled and its rider have a mass of 46.4. Sled is pulled across a frozen lake, so the force of friction between the sled and the ice is very small. Okay, we're going to assume that friction is negligible, so it's 0. What force is required to accelerate the sled at 3.45 meters per second? Let's start with drawing our free body diagram. If the sled is resting on something, that means it must have what vertical forces? And what? What's the last one? The up one. Normal. Okay. Is the sled moving up and down at all? No. So what should these two forces be drawn like? Equal. Okay. And then what's our last force that we're missing here? The pull, the applied force, or the sled that's being pulled. So we'll just call it the applied, or F applied, or pull, or whatever you'd like to call it. Okay. Assuming that friction is so small it's negligible, we don't have any friction, we're not looking at any frictional forces, what force is required to accelerate the sled at 3.4? What component or what direction does the sled have to be accelerating in? Horizontal or vertical? Horizontal. So that means we really don't even care about these two. We're only looking at our horizontal, okay? So our net force in the horizontal direction is going to be equal to right minus left. So our rightward force is our applied force. What leftward forces do we have? None. So you can write minus 0, you can leave it. However you choose. Okay, now we can do our substitutions. Net force is also equal to what? Mass times acceleration. And we're solving for that applied force. Okay, because it says what force is required. That's talking about that applied force that we're trying to find. We're trying to find this applied force right here. Okay, so we know our mass and we know our acceleration. Mass is 46.4. And acceleration is what?
3.45.
Okay, and that equals our force. What'd you get? 160.08. What units does it go with? Newtons. That's that applied force. All right. So if we look at part B, it says a force of 150 newtons applied to the sled and produces an acceleration of 3 meters per second squared. What is the magnitude of the force of friction that resists the acceleration? Okay, so we're looking at the same sled and rider, just a little different situation. So we draw a new free body diagram. Okay, we're still going to have gravity, and we're still going to have the normal force that are equal to each other. This time we're going to have an applied force or a pulled force. And we're also going to have one other force. What is it? Friction. Okay, so we are looking for the force of friction. That's what we're solving for, is F sub F. Are we looking at horizontal acceleration here or vertical? Horizontal. So we don't really care about these guys. So our net here, what's the net equation going to be? Tell me what it should look like.
F applied.
Very good. F applied minus force of friction. Okay. Yes.
Like on the first one we used, we found that
Okay, so now we can do our substitutions. We know the net force is also equal to what? Mass times acceleration. We're solving for the frictional force. Do we know the applied force? Yes. What is it? 150. We're going to solve for that frictional force. We know our mass because it's the same sled, so it's 46.4. And we know our acceleration because they gave it to us right here. So now we just do our simple algebra to solve for the force of friction. What'd you get, Matt? You don't have your calculator?
I have my calculator.
Okay, do you have a question?